All right, let's give it another 1 minute. Looks like a perfect day for taking attendance.
It'll probably be worse on Friday.
Because of the holiday?
Yeah.
Oh, actually, Friday is a very important lecture, so we have invited the first author of RF diffusion to give us an invited talk. So if possible, like, I would definitely recommend.
Is he from MIT?
Yes. Already, I think we can get started. So yeah, so this is the third lecture in the diffusion flow matching for protein design series, and today we're going to talk about a very important modality or extension of flow matching, which makes it very effective in protein design. And in the next lecture, our guest lecturer will talk about the detail about how these models are leveraged in designing protein backbone structures. And so just a recap, like last time we talked about diffusion and architecture like UNet, which is kind of the previous generation of architecture. So for flow matching and diffusion, what's important is this kind of shared score network, which takes the input of a current position, basically the feature space, and the model predicts the noise or the direction or vector field or score, where basically how you make changes to the current input to move kind of along certain vector field defined by the underlying distribution. So an important feature of the architecture is it has to be aware of the time, and it needs to adapt its weight based on the time. So how this is done in the UNet is you take T as an input and you do some time embedding, and then you concatenate that features with your intermediate layers. At each layer, you just do cross attention or treat them as basically additional features. So the time embedding will inherently influence your predictions on the next time step. So a more recent architecture is called diffusion transformer, which is generalizable to flow matching as well. It's a transformer-based model that which do not employ convolutional architecture anymore. It's kind of an equal length architecture that is more flexible, and you can generalize to like sequence data with flexible length, and still employ the key kind of state-of-the-art architecture with attention blocks. So the major modification to the attention block is previously you just take the features and do normal kind of multi-head attention and like point-wise feed forward, like the nonlinearities. But here instead we do additional modifications to these layers by adding these what they call adaptive layer norm architectures that takes the time step as an input, and you do the similar type of time embedding. And we take the time embedding and we train a embedding network that specifically predicts the scaling factors that will be used to scale and shift the intermediate activations in this attention before and after the attention layers, and also before and after these multi-layer MLP point-wise forward function. So you can assume this is kind of like last time we talked about like different time step, you want to focus on different levels of details and noise, right? So these scaling and bias added to these intermediate features effectively does the adjustment of kind of the noise level that you're learning. So it is proven to be more effective than the cross attention naive approach, and that's used in UNet. At least in a bunch of the image generation tasks, such network proved to be quite effective. Although in the protein design, I think the effectiveness of DIT might differ from task to task. So sometimes it may not be the best inductive bias for like flow matching tasks on maybe like 3D coordinates or backbones. So it's really it's a design choice that you can make where you could choose to include the adaptive layer norm, or you can just do the normal cross attention. And sometimes the the cross attention may work even better. All right, so we kind of talk about the diffusion as a continuous time stochastic process, right? Instead of doing the discrete Markov chain Monte Carlo, we can define a stochastic differential equation that is driven by both the score function, which is the score of the underlying distribution, or basically that's the force defined by certain energy, and this additional like Brownian motion, basically the stochasticity added at each time step, which mimics kind of the Langevin dynamics procedures. And therefore, we can define the training with the training normal loss that we do regression on the score. The only difference is in the sampling time, we run this SCD simulation as opposed to do the MDP, like the Markov chain sampling, as in the discrete case. And what this is done is by using the Euler-Maruyama solver. It's an extension of the Euler solver for ODEs, but additionally, there are good adaptive solvers which can kind of adaptively choose the time step, the step size you go forward in the trajectory, or you can use like a fixed discretization during inference time. So this is the basically where the diffusion model kind of converge into an SDE process, where the score controls the stepwise noise or direction that you kind of move your samples. And last time we talked about the continuous normalizing flow, which originated from completely different mindset of normalizing flow, but when we generalize it to the infinite time step and again continualize the multi-layer normalizing flow, we arrive at this ODE framework, which we call neural ODE or continuous normalizing flow, which shares very similar characteristic where instead of defining the score over the probability, we have these directly defined ODE of the trajectory of where the sample is at, and we're using that. And the generative model basically follows the ODE to directly move samples from the initial noise towards the target distribution by following the ODE defined in this function. And more particularly, you can see that this is, instead of learning the score, we're learning these more general kind of vector field, which is again a vector defined in all positions for all time steps. And starting from some initial distribution like a Gaussian noise, and following after you draw a sample, if you follow this ODE defined by this vector field, where the vector field defines the derivatives or the speed at each point where you should move. At the end of the simulation, you will end up having arrived at a distribution at t. And if you train this with the flow matching laws, we can prove that the distribution with the trained vector field neural networks will be very close to the actual joint distribution of the samples. So the key equation for telling us what how distributions are transformed along the ODE path is this continuity equation or continuous change of measure or change of variable equation, which we derived last time for discrete normalizing flow. And in the continuous case, we show that the change of the probability along the path is also follows an ODE that is defined by the divergence of the vector field applied on the probability density at each t. So basically, if we will solve this ODE path, we will we'll be able to keep track of the exact likelihood change of a given sample in the trajectory. So directly training the likelihood by solving this equation is very expensive because it requires solving these very expensive push forward functions with this divergence, which is mostly like the trace of the Jacobian, which is quite expensive, and therefore it's not the best way of training it. So similar to diffusion, where you instead of kind of doing sampling for all time steps and try to estimate the final likelihood, you match the score. And similarly here, right, instead of matching this likelihood, we instead match these derivatives of the flow that defines the flow path directly. So instead of maximizing the likelihood and solving that ODE likelihood, we directly say, like, if I can match the vector field for all points at all time, I basically have the ODE that is able to generate the probability that I want, as if I follow the continuous normalizing flow that is defined by this continuity equation and the corresponding vector field. So the intuition here is like we're matching the vector field similarly to we're matching the score function in diffusion. And the difference here is that the score function it's different from the vector field, and the vector field can be more general, and basically any kind of interpolation between two probabilities, which we will be able to derive the exact form of a probability and the derivative of that probability, we basically can control what the ground truth of that vector field is. Versus for the score, it requires more delicate assumptions about the noise that you're adding at each time step. So we can do that very expensive calculation from that arrived at the score estimation that only rely on predicted noise. And another thing is, although like matching this vector field in the marginalized distribution is what we actually target at the end, it is not tractable. Similarly, in diffusion, the marginal kind of the score distribution is also like intractable. So you kind of do this variational inference where you condition on one sample and you try to invert it back to the intermediate steps and train a loss that is on these conditional probabilities and marginalize it out on the samples. Here, the similar trick was used for the vector field loss, where instead of directly regressing on this intractable marginal vector field, we train our vector field loss with respect to the conditional vector field. Basically, we can define the tractable conditional probability path if we pick a final target point and we define the conditional probability path as the path of moving from a Gaussian distribution or the source noise distribution towards the delta function defined over that single data point. So yeah, and the key theoretical kind of contribution that motivate the conditional flow matching loss is that even though the first loss is intractable, if we train with the second loss, they have the exact same gradient and they will converge into the same optimum. So even though we're learning on the conditional vector fields, but because of the marginalization and the L2 norm of the equations, we'll end up being able to prove that these two laws have a similar exact same gradient. And we can effectively use the second loss, which is tractable. So the problem then becomes like how we come up with this like ground truth conditional vector field ut x given x1. All right, so as we talk about what this probability path means, right? It's basically at every time step t, you define what your samples, what distribution your sample should follow, and you also given that derivation of the probability, we should also have a tractable form of the gradient of that probability, which will define the corresponding vector field. So that's kind of the mindset that is used in defining the underlying ground truth vector field. So we basically want to try to find a path between the noise and the pure data points, and we try to come up with a series of function that's defined for every t, such that we know where the xt is with that function, and we also know what the p of xt is with that function, and that the derivative of both is tractable. So one way that people find super easy to track is Gaussian paths. Basically, at every time step t, if we can define a Gaussian probability that is depending on just the timestamp and the beginning and the ending of the trajectory, and we can define the mean and the variance of that probability path with certain kind of linear functions, then we will be able to compute exactly where the x is given the t and the x0 and x1. And we can also derive the probability of we can also define the vector field, which is the derivative that's taken with respect to this function of t. So then we get the kind of all we need, because what we need is this conditional vector field. And we don't need to even need to prove that this is a legitimate vector field, because we know that this is derived from this Gaussian probability path, where at each time point it's a legitimate distribution. We make sure it's a legitimate distribution. And the derivation can be, you can look at the derivation from the paper that with this kind of defined Gaussian probability path with this certain noise schedule on the mean and variance, we might make sure that we can easily derive the ground truth conditional vector field in this form. And basically, it's a question of choosing the form of sigma t and mu t that will be used to compute this ground truth data, which will then be fed back into this training loss to train our V of t. Is everyone with me so far?
So just taking a step back, the original flow problem was difficult. So then you moved to a marginal. You said instead of match the original ODE, let's look to match the vector fields.
Yes.
And then after that, you said, well, the vector fields are intractable, but if we conditionalize it, they're tractable.
Yeah, if you condition on the single data point, then it's tractable. And if we do it for all pairs of noise and data points, and they show that if you do it for all pairs of noise and data points and take the expectation of that loss, you expectively get the same gradient for the true marginal vector field that we want to learn, which is actually intractable. Okay, so if you look at this process, right, it's actually quite general. Like basically, you could consider this probability path definition being try to find an interpolation between x0 and x1, and if you can come up with a function that interpolates between the 2 points, you're making sure that that function will lead to a legitimate probability at each time t, then we'll be able to use that function as a ground truth to compute the as a target for our regression tasks. The first one is very simple. You can come up with all different interpolation, right? The second one is not easy, right? You have to make sure it's a legitimate probability, and you're landing exactly at the x0 distribution at t0, and you're landing exactly at your data point at t equal to 1. And this is why we cannot just come up with a random interpolation and use that, because we have to also make sure that such interpolation defines the probability path that follows the underlying assumption. All right. Yeah. So here's another demonstration of why this marginal probability path is easier to define, right? So basically, we want to find at t times 0 the probability path with x0 directly sampled from the p of x0, and we want the endpoint being a delta distribution where all of the mass is focused on x1. And we found that the Gaussian probability path, if we can define the sigma and mean, we'll be able to uniquely define this path. So we can get the probability path, conditional probability path, and then effectively the marginalization over the vector field loss will give us also the marginalization over the data distribution. So at the end, we are able to sample just from the noise without conditioning any endpoint. And we can directly sample from noise and use the marginalized vector field to draw the sample that is sampling from the entire data set and not just a single data point. So yeah, I think I think in the P set we kind of come up with the 3 different probability paths. All of them are Gaussian paths, The only difference is how we define the sigma and the mean. And we actually found that the similar paths defined in diffusion have exact same correspondence in one of the probability path here. So including the one of them called variance exploding paths, the other is variance preserving paths. So all of them will make sure that you move from a random noise to a single point. And when you move along that line following the distribution here, you know exactly where x is. There's kind of the formal solution of where x is, starting from these Gaussian assumptions, and therefore you can derive again the derivative of that flow is basically the vector field and the speed of how you move your x, and at the end you arrive at the ideal distribution, which is the delta distribution on the data. But these two paths, if you look at the homework, they are not very clean. They're like mathematical formulation of where x is, basically the flow, and what the vector field is for the flow. It has like a little bit more complex form. So what we found effectively that empowers the simplicity of flow matching model is this new probability path called optimal transport path, which basically, instead of mimicking what diffusion does, it directly defined a path from the noise to the target point, basically just linearly shrinking and moving towards the final point. So yeah, I think so. This might be a little bit difficult to understand, but you can see that in the diffusion, right? Because you need to add Gaussian noise at each step, so you won't be able to get such OT paths, right? Because you have to kind of increasing things, enlarging your variance, and then based on where you are in that variance, and you kind of need to crop it again. So it's essentially not very likely in diffusion that you can go follow that OT path, but because in this case we directly defined the ODE between the source and the target, we can arrive at this very nice OT path by directly defining where the points are, defining basically mean and the variance at each time step, and we can also follow the exact trajectory that will give you such kind of linear shrinkage of the distribution. So basically it will look like this. I have a better demonstration. So basically this is how, if you visualize how the points will move following the OT path and diffusion paths given the conditional vector field. So the one claim that optimal transport paths that empowered flow matching is more advanced than diffusion is that you kind of directly shooting at the target point without going over, or we call overshoot, and then go back. And such kind of behavior gives you smaller kinetic energy. Kinetic energy is defined as like how much movement you need to make to move from one distribution to the other distribution. And in the Wasserstein distance definition or optimal transport definition, you kind of want your movement to be minimized. So you're matching the distribution with the most efficient path. And we can see that this kinetic energy defined on this, if we look at the kinetic energy, we can arrive at the finding that the OT path is basically the fastest route that you can move from one point to the other point without going around. But just to know that this is kinetic optimal for conditional probability paths and not the marginal probability path. So if you look at the marginal probability without condition on this red point, it will look very different from what it is right now, because basically if you have one point here, right, you have a vector field towards that point, and if you have another sample here, you have a vector field towards that point. And if you kind of taking the expectation of the two, right, you kind of ended up in somewhere in the middle. So you will actually ended up having a curved vector field when we marginalize out all of these conditional vector field. But the visualization is kind of very straightforward if we look at the conditional vector field.
Intuition looks similar to diffusion, so why doesn't, like when you marginalize?
Both the diffusion path and the OT path are defined over the conditional trajectory.
Oh.
So both of them you don't know, we don't we cannot track what the marginal score or the marginal vector field will look like. Both of them, we can only track it when we explicitly condition on the final point, either in the variational setting or in this conditional loss setting. And this is kind of the trick that we use to solve that intractable inversion problem, where we know that exact inversion is impossible, so we kind of, using this variational matrix, we condition on the latent state where you project to the final state first and then project it back. And such derivation, like Albo derivation, is strictly bounding the likelihood in diffusion, but it's not available for flow matching at the moment. So even though we have this nice conditional vector field loss, the relationship of that loss with the Albo of the likelihood is still unclear at the moment. And we believe it's intractable. The Albo is intractable for ODE, is available for the SDE, but the form of the loss looks exactly very, very similar. Except that when you compute score, you have to follow a certain corruption scheme. I think this is the right timing to talk about the difference between flow matching and diffusion is, so basically in flow matching, in diffusion, they are following the similar kind of variance exploding and preserving paths, but this is because only basing on such kind of corruption schedule, you'll be able to get the closed form score from the SDE formulation. So this is essentially very limiting because the underlying probability of the SDE follows a different push forward equation called but that equation is more limited. I think I have that somewhere. Anyway. So if we really want to solve the diffusion in kind of the flow matching way if we really want to view diffusion in the flow matching way where you try to track the change of the probability, right? It's actually much more complex than what we get in flow matching, where it only depends on the divergence of the flow, divergence of the effectively taking on that probability mass. But the actual dynamics of the probability evolution follows a much intractable, I would say intractable dynamics, which is fully under this Fokker-Planck equation, which probably motivated from physics again. So therefore, I think that's kind of why for diffusion you kind of have to define a very particular types of corruption scheme and probability path, such that you can get away with the intractable terms in the score, like the score estimation. So in the flow matching, I'm not saying that it solves all the problems. Of course, like we said, you can't just randomly define an ODE and say it's a flow, because we have to make sure that we know how to keep track of the likelihood, right? And the reason we want to keep track of likelihood because we want to make sure at the end of the trajectory we're arriving at the right distribution. So for flow matching, I think flow matching is more general than diffusion in the form in terms of the form we can assign to the probability path. So you can see that OT transport, the optimal transport path, is one example, and people are also try to think of a creative way of doing the pairing of data and noise differently to enable a potentially more flexible distribution. And you can also, there are even more advanced stochastic interpolation that is defined between different distribution other than the Gaussian noise. But in short, it is more general in terms of how you can define probability paths to make it a legitimate probability path. And it is also generalizable to other manifold, which we'll talk about next. So in terms of the more general source coupling, so if we look at the conditional probability paths, right, what we're sampling here is you kind of want to define an initial sample, which previously we defined it as something that's irrelevant to x1, right? It's completely noise. and the target point is the delta distribution. But effectively, we can always treat this P of 0 as a marginalization of the conditional probability times the distribution of a simple x1. So we can always like marginalize out x1 by drawing from the joint distribution of x0 and x1 instead of always drawing completely random like from P of x1 independent to x1. So this is indicating that you could, instead of always treat x0 and x1 as completely independent, we can inherently inject some dependency if we know that there are certain pairing that could further minimize the kinetic of the transport problem. So a small change that's made here is like basically how we sample how we make these samples here. So instead of completely randomly sample from x0 and independently from x1, you can imagine this step being replaced by defining some joint distribution of the pair of x1 and x0, and that does not change the marginalization guarantees and all of the important equation that arrive at the conditional probability distribution loss. So one such trick that is applied to give you a slightly different pairing is called mini batch OT, or mini batch optimal transport. What it tells is that basically during training, you can essentially sample a mini batch of x0 and xt. Even though you can completely sample them independently, you can construct pairs within the batch during the training such that the pairing of x0 and x1 is no longer fully independent. So this is basically solving kind of a small optimal transport problem within that mini batch, such that only points that are close, right? If you have some point here, 2 points here and 2 points here, then basically it's not very ideal if the two kind of vector field cross over, right? Because then if you marginalize it, you have something in the middle where it ends up being pointing at nowhere. So you could rearrange the pairing such that you can directly assign this point to this point and this point to this point, so you have non-crossing over ground truth vector field, and that could lead to a better optimal transport behavior and maybe easier to learn, because you kind of artificially splitting out where your samples are and let them to make smaller movement towards the points in the data. So this additional step of reassigning pairs by computing certain cost function over the distance maybe, and coupling them together, and then compute the ground truth vector field loss, conditional vector field loss will effectively give you kind of a better separation. So this is one example, kind of intuitive example in the mini batch OT paper, where you kind of avoid going through this crossing over pass, which will create kind of statistically like harder to optimize ground truth, and you kind of having this shorter pass and globally like more like optimal transport like distribution at the end. However, empirically, when we use mini batch OT, we have one observation that because we're training the neural networks for across various tasks, and sometimes we don't just care about unconditional generation, but we want to condition on certain properties or attributes and do like conditional generation. And so some of the generation problem, like for the flow matching model, you can explicitly train the model to condition on certain input. For example, text to image, right? Text can be treated as a condition, and your model can adapt its vector field based on what text instruction is given. So in this case, we actually have some observation that mini batch OT kind of hinders the generalization to other prompts and conditions, because this, imagine this pairing of x1 and x0 can also be highly condition dependent, and deliberately like assigning this based on trained conditions could hinder like better generalization, because in the real case the new condition, they may employ a different structure, and therefore the pairing is completely broken. So and in that case, like fully random and independent pairing actually gives us better guarantee for generalization. But in practice, if you care about unconditional generation, the mini-batch OT is a very effective approach that will speed up the convergence of your flow matching models. All right, so the most important and attractive point of flow matching, I believe, it's not because the OT pass in the Euclidean space, like image. So you can see that in the image generation, majority of the paper are still using diffusions, and even if you switch to flow matching, like in Stable Diffusions 3, like a lot of the tricks technique talked about here is still like generalizable across diffusion and flow matching. So I believe the most attractive point of flow matching resides in a different perspective, where it's actually easier to generalize to non-Euclidean space. By non-Euclidean space, we're kind of what we define as Euclidean space is basically this unbounded plane, flat plane, right? Where the shortest distance between 2 points is the straight line that connecting 2 points in the flat plane. And therefore, all of this interpolation that we defined, following this kind of nice linear interpolate of the coordinate of 2 points in this Euclidean space. I mean, the flat plane is just like one example of 2D space, Euclidean space. You can also imagine like the 3D Euclidean space being the space that's defined by the 3 orthonormal bases, Cartesian basis that we talked about previously, right? So any distances in that space has like a very well-formed formulation, which we call L2 distance or L1 distance, which you subtract the coordinates and either take the absolute value or the square of that, and that gives you a legitimate shortest distance metric between the 2 points. However, there are a lot of there are more general types of geometrics. Most famous one is Riemannian geometrics. So where there you can imagine kind of a curved space or curved plane, such that if you only if you constrain yourself to move along that curved space, you no longer have the same way of computing the distance between 2 points. So like this is kind of one example, like with the sphere, or you can imagine the Earth, right? The shortest path from one point x0 to x1 right now is no longer like if you're allowed to only travel on the surface of the Earth, you cannot go like inside the undergrounds and drill like a hole between 0 and 1. So now the shortest distance you can travel from 0 to 1 actually resides on that kind of circle where the circle is passing the center of the sphere. And such curved geometry is very important because in applications like protein design and like robotics or small molecule design, there is one key metric when we talk about geometric deep learning is rotation. So if we try to simplify the representation of the geometry of the molecules, like remember we talked about the frame representations, which effectively simplifies the degree of freedom into translations and rotations, right? And similarly, when we talk about representing geometry of small molecules, you can also uniquely define the geometry with the combination of bond angles and bond length and the dihedral angles. So angles and rotations, these values, like effectively they reside on a manifold that is different from the Euclidean manifold. Therefore, the distance and interpolation on this manifold will require a slightly different design. And this is kind of the place where flow matching shine, because when previously there are a lot of difficulties in modeling, building generating models on these Riemannian manifolds, where you kind of have to come up with some way of projecting the non-Euclidean space to a certain Euclidean space. But the operators that you define is like the properties of the operators that you define in those spaces essentially different, and therefore you kind of ended up not having very nice and closed solution that can treat all possible like cases that you encounter in the manifold to Euclidean space mapping. Like similarly for diffusion, like if you look at a Euclidean space, which is the kind of naive form of diffusion that travels in the Euclidean space, right? Everything, this kind of Fourier-Planck equation is defined in the Euclidean base, then you have this known like exact form of certain like key values like the conditional scores. But if we kind of look at this in the curve geometry, then this model then the diffusion process need to be redefined using a geometric random walk, and the corruption and inverse process of that is essentially very hard to compute, and basically there's no closed form solution exists, and you have to do very expensive approximation that will increase the statistical errors and also lead to very undesirable optimization behavior. And it's just too complex. So instead, if you look at the continuous normalizing flow setting, right, you can basically think about the ODE path between the beginning and the targeting points as kind of traveling along a path or along the line that gives you the direction to go. And the OT path, especially the optimal transport path, right? When we look at the optimal transport, conditional optimal transport derivation is effectively a linear interpolation between x1 and x0, basically suggesting the shortest path between 0 and 1 that you follow in solving the conditional distribution, conditional probability path. And similarly, we can also treat if you can, which is saying that if you can design such a vector field, you can also easily track its probability with continuity equation, and the continuity equation is defined in this form, which is currently we can look at this form in the Euclidean space, but if we look at what's inside this form, it's actually you can consider this divergence being the volume of the outflow at a certain point, where it's kind of the density at the point times by the diffeomorphism you applied to that density. And that diffeomorphism or the volume is actually also definable, or it has closed form solution in several geometries. Like for example, in the sphere, we actually know similar derivation of the volume of the outflow, and therefore kind of the nice mathematical relationship of these interpolations and the tangent space and the divergence on the known Euclidean and Riemannian manifolds gives us the opportunity to basically take what's valid in the Euclidean space and map it to the Riemannian space by simply replacing certain key operators, which for the computation of that operator we kind of know the closed form solution. Particularly what's important here is instead of moving in the plane that instead of kind of moving in the plane, in the flat plane, we want your vector field to always reside in a tangent space, which is used to define the movement over the curved geometry. So for each curved space, you can imagine each single point, if you look at the tangent plane or space in the higher dimension, there's uniquely like one tangent plane that all of the possible directions that will enable you to move in the short time step within that curved geometry resides on that tangent space. And the key thing is to just always make sure that we come up with the derivation with the form of the vector field such that we know that it resides in the tangent space. And we also know, like, in this Riemannian space, we replace the divergence computation with the equivalent in the Riemannian space. So this kind of divergence is also defined for some certain types of the Riemannian manifold. So given these two, we basically can assume that, like, if we can define a vector field with the interpolation, with a similar interpolation scheme in the optimal transport path in the Euclidean space, with a similar equivalence in Euclidean space, we will be able to rewrite our training objective function. So now the divergence and the distance we changed the metric from L2, which is Euclidean distance, into this new Riemannian space. And we're using the Riemannian metrics to measure the divergence and the distance in the new space. So yeah, so I think a lot of the intuition remains the same, right? So assuming this is our manifold, of course this is an ugly one, but for like the unit ball or sphere is simpler. But the high level idea is still like try to match the conditional vector field and compute what the conditional vector. To compute the vector field, you basically want to define the routines or the routes for the points to travel. From the starting points to the sample, conditional sample points, such that at the beginning you start from some distribution and at the end you arrive at that single point. And taking the analogy of the vector field in the OT path, which is the shortest distance in the Euclidean plane, here we introduce what we call geodesic, which is the shortest line on the manifold connecting the 2 points. So we basically define the flow as the direction or the trajectory that follows the geodesic defined over that manifold. So the geodesic is, as I mentioned, like the shortest kind of line that you can follow to travel from one point to the other point. And to define that, you need to define metric, which you can consider metric as like a form of distance, right? If you know how to compute distance between the point, then you know what the shortest distance is, and you know where the shortest distance direction is. So in the Euclidean space, we see that these shortest geodesic is always the straight line between 2 points, right? So we do this linear interpolation with respect to t, so we can get a straight line. We move along this straight line between x0 and x1 for any given t between 0 to 1. And more specifically, you can define a different time schedule where your time does not improve like linearly, but following some schedule where you can like jump or go faster at the beginning or go slower in the end. But it doesn't matter because everything is traveling along that geodesic. And similarly for the Euclidean space, we can define the geodesic as with the exponential map and log map. So kind of log map is kind of like the division or kind of like division, and exponent map is like multiplication. So you can consider this as being a new types of interpolation from x0 and x1, such that when t equal to 0, you are at x0, and when t equal to 1, you arrive at x1. And the t uniquely defines the interpolation from x0 to x1, such that if you move along that line defined by this log map and exponential map, you are moving along the shortest distance path, which is a geodesic. And such path has a closed form for simple manifold like sphere. So this is the exponential map and log map defined on the sphere, and you can also derive similar map for several like known manifolds like hyperplanes, hyperbolic space, and a few other manifolds. And the training, like if you look at the previous like training of full matching, where you kind of define these CalT, which is the schedule, you can define similar thing here, where you can basically, instead of doing going linearly from 0 to 1 in time, you can maybe forward the time faster, but basically like you can freely design the noise schedule, so you can decide the speed that you travel along this line during the training. Okay, and everyone's with me so far? Like again, these maps are designed such that they are tractable in the Riemannian manifold, and we know what their divergence is, and we know how to track the likelihood, and we know if we follow such flow, we are reproducing a probability path. So this simplicity form, it only has this kind of form for certain types of manifold, and not on all like arbitrary manifold, unfortunately. So if we want to do those kind of simulation-free like flow matching training, we can only use it for certain types of manifold that we know solution for, and rotation is like the SO3 manifold, or rotation is one such manifold. So there are solutions to very complex, like general manifold like this. So where you kind of know that there exists certain geodesic, but you don't know the exact form of interpolations. But still, like it is possible to simulate trajectories and solve with as long as you have the distance metric, which we call pre-metric. In this case, the pre-metric doesn't have to be the same type of metric like the norms in the previous established geodesic, but the pre-metric only need to satisfy the following conditions, which are kind of like the distance, but slightly different assumptions. And it is shown that you could still simulate the shortest path by solving kind of these equations, the differential equations. So if we truly want to train a flow on a more general manifold, it will be more expensive and will end up being more like a simulation-based training, like the previous neural ODEs. But that says it's still like flexible and tractable. If like compared to diffusion, it's almost impossible like to do such kind of simulation. All right, so in terms of pre-metric, so in terms of pre-metric, I mean, in this example, they define what they call spectral distance, which is basically a weighted sum of different eigenfunctions of the spectromic operators. And it's kind of like a generalization of like a certain Fourier operators defined over these curved complex manifolds. And this omega is kind of the weighting that you add in front of these eigenfunctions. And so it's kind of showing that with the proper choice of this kind of pre-metrics and scheduling, it's able to perform pretty well in certain cases. And the types of weighting and the basis that they choose at the end that they found to be the best for solving complex geometry problems is called biharmonic. But essentially, it's not following the shortest path like a true geodesic, but instead it has like a better, nicer property, even though it's not following the shortest path. You can see that, for example, in the cases where the manifold is very like complex and have a lot of boundaries, following the shortest geodesic may causing this kind of bottlenecking issue where you have tons of points stacked in the similar track in the similar boundary or corners, versus using this biharmonic pre-metric, it's kind of able to get around with boundaries, so it performs nicer and works with better actually than the ground truth geodesic, and they kind of show the effectiveness of that method on these general manifold. So I would say like this is a very phenomenon and important paper in the field of flow matching. So whether you work with complex geometrics like this, or you like point cloud, or like shells or density maps, or you work with more like well-shaped manifold like sphere, right, or torsion like torsion towers, I think this is a really good paper to read, and that will be also one of our reading assignment. Actually, and the thing is, like, if you look at the diffusion models, we have to do approximation of the scores because there is no exact form. Even with simulation, there is no exact form, and therefore this approximation that they take with this kind of also again using the spectrum, the eigenfunctions, could also introduce a lot of bias. And so effectively, they found like for the similar types of manifold or problem, like flow matching is always like very elegant because it requires a small number of eigenfunctions to achieve like very accurate simulation and approximations. We don't need to look at it in detail, but in the high level, like for Riemannian diffusion, instead of using like the previous, like the drift, the simple like drift functions and the like Brownian emotion, you have to follow like certain complex noise called heat kernels. And the heat kernels also is only approximation of of the true like random walk in the geometry. And if you look at the actual routines for Riemannian diffusion, it is way longer and sophisticated, and also like the intermediate step is inaccurate approximation, so it always ended up like being both inefficient and inaccurate. And in terms of, instead in the flow matching, we basically don't change anything, right? It's exactly the same as Euclidean flow matching. The only difference is like when we sample the training example X and noise, we do a slightly different interpolation. So with the known manifold, we can do this log map and exponential map interpolation, and we just try to like derive, and therefore we can get the the exact like ground truth vector field, which we again have the closed form deriving from the divergence of the vector field. So essentially the whole training loop remain exactly the same with slightly more complex objective. And time complexity also remains exactly the same. But sometimes when we optimize with Riemannian geometries, we found that the noise schedule could be different from like what's optimal for the Euclidean space. So for example, instead of uniformly sampling time linearly from 0 to 1, people sometimes found like exponential time schedule, like maybe moving slightly faster in the beginning or slightly slower in the beginning would help the model to learn better. And that is also like some kind of ongoing discussion that there isn't a clean solution yet, but I think it's something that in practice we want to figure out. Okay, so yeah, I think this is just some results. Yeah, so I think the major takeaway for flow matching is it's able to enables the use of a very efficient and elegant parameterization, and it's generalizable to general manifold, and we know the solution for multiple manifolds such as spheres, and therefore it enables general modeling for proteins and small molecules that involves rotations and like torsion angles. And it's completely simulation free if you know what manifold, the manifold you work on is simple. So there's like a preview of the next lecture. Like the flow matching and also diffusion has actually shown to be very effective in the protein backbone design tasks, where in the AlphaFold problem, we kind of try to solve the structure folding problem. For a given sequence, we solve what the structure is, right? And in this case, we're kind of trying to directly design the backbone structures without knowing the sequence. So we kind of try to build a diffusion model that will generate these 3D shapes of frames that also have translation and rotations, similarly to the structure prediction models. And we're applying the Euclidean flow matching on the translations and SO3 flow matching, or Riemannian flow matching on the SO3. And jointly, we kind of we were able to sample a protein backbone efficiently. And similar works for small molecule, although sometimes you don't care about angles. You can solve that with like Euclidean space models. So yeah, so next lecture we'll invite Jason from MIT, who's one of the leading author of RF diffusion, to give us kind of a comprehensive discussion on that. Questions?
Yes. So for the first case, what's the base manifold that you see?
So it's sphere for rotation. So sphere, yeah, SO3 for rotation, and torsion has like a torus like there's like a manifold called torsion torus, which you can map it back to Euclidean manifold essentially. So like solving geodesic in torsion torus is very similar to solving Euclidean geodesic, but the
how do you know the geodesic path on those?
So the exponential map, yeah. So you basically can find this exponential map.
That's for any general manifold?
No, it's only for rotation. So this is only for SO3. The sphere, the basically unit ball. Yeah. Okay. So the another extension of flow matching and potential diffusion is across the modality too. So if you notice that all of the discussions we had so far are based on Gaussian assumptions, right? And they're most likely designed for continuous space, like the coordinates or pixel, like the continuous value for pixels in the image, and rotations and translations. Those are all continuous modalities. But in the real world, we also see a lot of discrete data, which we talk about a lot in the first half, like protein sequences, right? Amino acid types, and atom type. A lot of the modalities in generation is discrete. So now that the kind of the continuous model, diffusion model, has the nice property of modeling the joint distribution without relying on the autoregressive ordering, there's also like a realm of study that try to look into the discrete modality and see if we could extend diffusion and flow matching to discrete modality as well. So yeah, this is the example in continuous domains. So indeed, there are actually multiple attempts to alter the autoregressive fresh framework for generation, potentially like whether using like this kind of using a diffusion model that mimics discrete jumps on the space, where so instead of following the continuous score and doing this continuous jumps in the space, you follow certain types of discrete Markov process. And then there's also we could also continuize the space, where if you're working in the probability space, like the probability simplex, we can consider that as a continuous space, and try to design flow matching or diffusion models to utilize the property of the probability space. So like again, the autoregressive models, they have of course been very effective in language models, where well language is kind of heavily, you can consider language itself has originated from the strong inductive bias with the ordering from left to right. And basically this causal relationship is very clear, and therefore it might be a good inductive bias for left to right kind of language, but it may not be the best for proteins or things that don't necessarily have that causal relationship at the end. And also subject to certain sampling exposure bias, and you can always expose from left to right, and you only always condition on seeing particular context when you generate things, which may not be ideal for other types of like joint distribution fitting. And it's also constraining certain architectures to be like autoregressive, and sometimes if you consider like a fully, index by index sampling, or token by token sampling, it has this iterative nature, although you could accelerate it with a lot of tricks. So the diffusion models, you can see that diffusion model is because it's defined over the joint space, joint feature space, right? It does not have the inherent autoregressive assumptions. And you could essentially move forward multiple positions jointly instead of doing like one-by-one generation. But still, like diffusion is an iterative generative model, because you cannot rule out things in one step, but instead you do it with multiple steps, and that significantly improves the result comparing the one-step rollout in like variational inference, in variational autoencoders. So basically the motivation here is whether we can leverage some of the good properties, the inductive bias in diffusion in modeling these non-autoregressive joint distribution, but also like make it try to make it scalable. So very naive way of doing discrete diffusion is directly continualize everything. So if we consider logits, right, the logits will uniquely define a distribution over a categorical space. So like a very naive solution is we just go blindly for a continuous diffusion, and at the end we just take an argmax, or we can sample. We can normalize the logits and sample from that, and that always gives us discrete samples, which is a very earlier line of work that already kind of, if you look at the kind of the like a protein generator, which is a follow-up of RF diffusion, they employ such simple choice, and it actually works already in the protein sequence design tasks. But definitely we can consider to make better use of this discretization process, and for example, like there are people to come up with discrete state jumps, like assuming that instead of traveling in a continuous space, we now have to make jumps between the distributions, between the sample space, and the sample is the transition between one discrete sample to another discrete sample follows certain transition matrix. It's kind of like the transition probability in the discrete Markov chain, and therefore we can come up with an alternative forward and backward process where in the forward we can make this discrete jumps and get certain type of corrupted distribution, and we again using variational tricks to do the inverse jump, which is again defined as certain transition probabilities. So for example, like one way of doing the corruption, designing that discrete space jump is by adding mask. So for example, you could essentially randomly masking parts of your clean data, and with significant amount of jumps, you ended up being completely masked sequence, and you can design the diffusion model to invert that process. And a slightly more complex version is to define random mutations jump. You have, or not random, but like your corruption process is based on certain rate matrix or transition matrix, where you could design that transition matrix to be maybe substituting something with something similar, or you can substitute with something completely different, or completely random, making random jumps. But the nice thing is like they kind of allow a more kind of hand-tailored mutation process. And in the sampling case, you start from maybe a random sample, right, and or some prior distribution, and then you can use the train a diffusion model to predict the jump, basically the inverse step, the reverse step in this model. This is slightly harder than the previous case, because previous case you know where the masks are in the reverse sample. You basically know where you want to unmask a sequence, a token. But in this case, you have also need to decide which position you want to make a change to. So yeah, we don't need to go to details, but like we just need to remember, like with basically you can multiply these transition matrices together to get the terminal distribution after making several forward and process, and you try to like make assumptions that such distribution follows certain prior distribution, and we again solving this with the reverse, with a model to do the reverse sampling with the variational loss. But still, like if we look at this formulation, it kind of deviates a lot from the nice formulation of the continuous flow matching and diffusion, right? And therefore, like you need to make tons of assumptions and designs of these rate matrices to make it work. And also, it's kind of harder to control like how much you deviate, because if you make discrete jumps, the jump can be very big between the steps. Whereas when we make this continuous move in a continuous time fashion, okay, so I forgot to mention that this also requires discretization of the time, which also like it's something that can be unideal, because the continuous time formulation really gives us more flexibility and power in modeling the probability path. So like the natural, and then one more thing is there's a recent paper called Evil Diff that basically applies such discrete diffusion on protein sequences, where they train a huge diffusion model on the UniRef protein sequences, and they also kind of together with the sequence, they can also do diffusion on the MSAs together, so you can kind of learn to unmask and generate the evolutionary information together with the sequence. In the case, you could, when you train the model, you can basically use it in different kind of conditional distribution tasks, where you can give it partial sequence and let it impede the rest of them, or you can condition on maybe certain MSAs or family information and try to diffuse the sequence. And this is kind of one demonstration of the discrete diffusion in the protein design case. But like if we're thinking about the nice properties of continuous flows, and the simplicity of doing interpolation and doing simple regression tasks, we're actually a lot that's not been leveraged in categorical distribution. So the other realm of thought, which is also like motivated one of our recent work, is called statistical flow matching, where instead of doing this discrete jump, which kind of breaks all the nice properties in continuous time diffusion and ODE. We instead try to leverage the manifold or the space of probability or categorical distribution. So in the end, we kind of want to define a generative model over the categorical distribution directly. So the space we're operating now is not an unbounded continuous Euclidean space, but instead this kind of bounded distribution space, where if we have like a categorical distribution of 3 values, right, you can imagine the probability of the categorical distribution over the 3 discrete state being lying on this simplex, where for any point on the simplex you have a normalized probability sum up to 1, but you were able to move towards like different distributions on the discrete space. So there are like multiple works that try to leverage such like continuous property over the probability space, but I think we found that it's actually, if we formally define the space of all categorical distributions, we're actually able to induce a very like similar structure with the Riemannian manifold that we talked about previously, like in the rotation, because so this is involving a little bit of the information theory, where so yeah, I think called information geometry. So basically, people try to define space for probability metrics, probability measures, like distributions. For example, categorical distributions, multinomial distributions, and there are prior work, phenomenal work by Fisher and Rao, that introduced what we call Fisher information matrix, which is essentially kind of the partial, I think the second derivative of the KL divergence. So it's kind of like the speed, the direction that towards which your KL divergence will be reduced in the fastest speed. So this is a kind of a very popular metric for defining the distance between two metrics. Distance between two statistical distributions. And there's also known kind of solution that if we define a manifold with the Fisher information matrix, where each point in the manifold is a probability distribution, like a categorical distribution, then we can show that such manifold is a Riemannian manifold, and the metric of that Riemannian manifold is Fisher information metric, defined here. And we also, the nice thing about that is with this kind of Fisher-Rao information matrix, we'll be able to derive like the closed form solution of the geodesic. And if we have closed form solutions, we kind of know how we can interpolate between the distributions along that Riemannian manifold. And we basically can apply what we learned today on the Riemannian flow matching. Another visual explanation of the difference of using the Riemannian structure compared to just treating these simplex as a linear Euclidean manifold is you can see that the actual like curved structures gives you like better derivatives in the boundary, where if you just assume like Euclidean assumptions on these simplex, you kind of have a similar kind of overshooting vectors at the boundary, and that's kind of stop you from remaining the legitimate distance within the space. And the other nice thing about employing that distance is kind of when you choose where to go, you kind of follow the metric naturally defined by information geometry. So the direction you go will you're basically pointing towards the direction that reduced your KL divergence, the gradients, the second gradients with KL divergence, which is called the natural gradients. And furthermore, there's also like known